you claim that there's no free lunch in data science and that data come with trade-offs. So what does that mean? What are the trade-offs that data scientists must be aware of?
If you think about the term data privacy itself, it's bluntly, it's an oxymoron term, right? Because data are born to review, and privacy means to conceal. And what I saw at the time is a need for people from all walks of data science. And we're going to talk exactly what do I mean by that later. That needs a forum to even debate with each other.
Xiao-Li, I'm so excited to have you on the Super Data Science podcast. Where are you calling in from?
I'm calling from Brookline, where I live. And thanks for having me here.
That's in Massachusetts?
I hope so. Yes, it is Massachusetts.
Nice. Easy to commute into Harvard. Do you have to commute a lot into Harvard these days, or?
I do, but actually, if you don't mind, I'm going to share a story because now it reminds me when I initially moved here.
Yeah.
Trying to figure out how long would it take for me to go from my house in Brookline to my office. Mm-hmm. So at that time, I just, there was a Yahoo map, right? So I just put in where my location is, where, my office is. And Yahoo come back, say it's 7 miles, away. Mm-hmm. But guess what was the estimated time of traveling from my house to there, provided by Yahoo map then?
In 7 miles? I mean,
7 miles, yes.
20 minutes?
Right. Okay. Now you're obviously smarter than Yahoo Map. At the time, it provides a number that I was just laughing so hard, and then I know exactly what they did. It was 8 minutes. Right. There's no way you can do 8 minutes go anywhere. I mean, we just get out of the garage here. But I was wondering, they must have done something like a 60 hours, or 60 mile, per hour. So 7 miles, 8 minutes. So it's a great example of how wrong things were then. But anyway, so the real travel, I hope so. Real travel is usually about, as people say, anywhere in the city, you go like 40, 45 minutes-ish. Although I have done 20 minutes, to be precise, 23 minutes, 3 a.m. in the morning. That I was able to do the 23 minutes. So.
Gotcha. So we were introduced by Dr. Amy Brand so she was in episode number 567 of the Super Data Science podcast. A really great episode about open source publishing. Mm-hmm. And Amy is the lead at the MIT Press. She runs the show over there. And she said that I had to talk to you. She said that Xiao-Li, she was like, he would be such a perfect guest for the show. And I instantly looked you up, and I've been excited about having you on since. So it's been a few months that I've been waiting for this interview.
Thank you.
It's so exciting to have you here. You really are an exceptional individual. So you are a professor of statistics at Harvard, which would mean that we would have a ton to talk about in its own right. And we are going to talk about some of your fascinating research in this show. But another thing that you do that our audience would love is the Harvard Data Science Review. So you're the founding editor-in-chief of the Harvard Data Science Review. You're coming up on your 5-year anniversary. Is that right?
Next year, yes.
Next year.
Exciting. Next year.
And probably close to Amy's heart is that it is an open source publication, open access. And so that means that any of our listeners can check out the episode. So tell us about the Data Science Review. Why did you found it? What is the niche that it fills?
Right. Well, thank you very much. First, I want to say that it is because the founding of the Harvard Data Science Review where I know Amy, and she has been tremendously helpful because Harvard Data Science Review is published by MIT Press. Now, I always have to tell people that does not say MIT and Harvard have merged, although historically someone have tried. It's simply because the Harvard University Press, obviously I went there first. They don't publish journals; they only publish books. But that gave me a chance to work with MIT Press. And you mentioned Amy being, the leaders in open source. That's actually something I want to talk a little bit about later as well. But let me first answer your question about how did we start to think about Harvard Data Science Review? And Harvard started to have a data science initiative, just like many other universities. Every major or even not so major university these days feel the need of the necessity to start with something on data science. So at the time, I just finished my 5-year term as the dean of graduate school here, and one of the co-director of Harvard Data Science Initiative came to me, and her name is Francesca Dominici, and she basically said, Xiao-Li, we know you are very creative. Give us some ideas here in terms of what Harvard Data Science Initiative should do, particularly going beyond Harvard, because most of these initiatives tends to be internal, trying to help the data science enterprise on campus. And but so I thought, well, I said I did have an idea because Harvard has the brand names on Harvard Law Review and Harvard Business Review. And what I saw at the time is a need for people from all walks of data science. And we're going to talk exactly what do I mean by that later. That needs a forum to even debate with each other, to know each other, to understand what each other is doing, to understand why we have so many different definitions or understandings about what data science is. So I thought that would be something. I know it would be very ambitious, but I thought they were asking for opinions. So I always have opinion suggestions. Of course, as you probably guess what happened next, after a few months they come back to me and say, Xiao-Li, we love your idea, but you need to do it. That's usually what happened. And I thought pretty hard about, and I did feel like this would be a very good enterprise to get into it, and so that's how I, started. And but I want to tell you, from very beginning, the mission of Harvard Data Science Review is very clear, very ambitious. I said if we're going to do this, we may as well do a big one. So our mission is really, or rather vision is really to define and help to define and to shape what data science is or should be. That's how I can tell you tons about Harvard Data Science Reviews because we have, our board is very broad because of our slogan is everything data science and data science for everyone. And so on my board, by now I think it's we have multiple boards. We have the editorial boards, we have an advisory board, we have early career boards, which we engaged young people. I think we have over like 150 people, and we have basically from philosophers, and I'm going to talk quite a bit about why philosophers is relevant, all the way to quantum physicists, to entrepreneurs, government, data scientists, government leaders. We basically really trying to cover everything data science, and it has been enormously rewarding as well as challenging, just because people from very different walks and even the way they talk about data science are very different. But that's exactly what we initially planned to do.
Cool. That sounds like a smashing success. It's amazing that only 4 years in, you already have so many different boards to work with and 150 people in really interesting, broad areas from philosophy to quantum physics. That's cool. And you've had some pretty popular issues already. So one big one with over 100,000 views was on the 2020 election.
Yes.
You've had a COVID special issue. You've had issues on reproducibility in science and differential privacy. I don't know if some of those topics, if you want to particularly dig into those, why was the election one so popular?
Well, I guess for obvious reasons, right? Because given the 2016 election prediction were, let's be modest, pretty disastrous, and I actually part of my own work is really emphasized on data quality. I can get into details later, but at the time that what we decided to do, we want to make sure that we publish special themes, before the election actually happened. So we basically had a variety of political scientists and others who are brave enough to put their predictions online, literally, and so we can verify afterwards. So we managed it, and also what's very interesting time wise was very very pressed because we don't want to people to predict too early, right? Because that's, that's hard. So we published literally it's like about a week before the election actually happened. And you probably know at the time everybody was so nervous about it. So we got lots of hits. And then we did some podcast later, actually, to follow up with these people who made a prediction and ask them, why did you get it wrong? Why did you get it right? So on and so forth. So when I look at tracing the readers, the clicks, you can see clearly there's a peak. We're talking about data science, right? That's what the signals are, just blips, huge blips. And so yeah, and so that's what we did. And the one on reproducibility and replicability of science, it was actually a joint venture with the National Academy of Science because they had a special report, I think back in 2019, and so we teamed up with them and we published that with a lot of interest. And the special issues on COVID, obviously, by the time I got locked down, that's what more than 2 years ago. When I saw that, like, what do we do now? And then obviously, given data is so important for all kinds of reasons, so we started to put together an issue. I think we had a rolling kind of base publications. We get people submitted, and we're trying to do as fast as we can. There was a lot of interesting challenges there as well, and so we started publishing in May, and the whole issue I think lasted more than a year. We could just keep adding articles. By the way, too, for any audience that this is completely free, completely open, and so please check, including now if you want to check now. So.
Nice. And so, in addition to the written publication of the Harvard Data Science Review, I understand that there's also a podcast, but that it's actually mostly just about marijuana. So I know that you have
yes.
a recent episode happens to be on legalizing marijuana, but you've also had episodes about whether we're alone in the universe. It sounds like lots of fascinating topics and probably digging into the data and the scientific literature behind particular topics.
Yes, thank you. And we do have an episode about marijuana, coming. I think just in a couple of weeks, and probably even sooner than that. Well, the reason we did the podcast is probably the same reason as you do the podcast, which is want to engage audience from all levels of interest and curiosity. And we so far have had, this will be the 16th episode, so we're very young. We do once a month, not like yours. It's like twice a week. That seems enormous amount of work. And but the topic we choose, obviously, we want to choose the topics where data science is relevant. But that's actually a very low bar because almost anything is data science relevant these days. But we want to choose the topics are of broad interest. And the way we did it, most of the topics we choose are related to a particular column we have in Harvard Data Science Review is called a randomness in recreations in randomness, and that's a particular column on data science for like leisure activities. And so we had episodes on wine, how to pick up a wine. We had episodes on sports, and we had the first episode was on matchmaking, and so.
Wow.
And right, and so we typically have these topics are related to an article or future articles that in Harvard Data Science Review, but talking a way that in a more kind of a plain language. We typically have two guests, and usually with kind of a complementary views. And as lots of these topics are easy to get people who have different views, but our emphasis has always been we want people really talk about data science, the evidence-based support, because as you know well, it's easy to be very passionate about something than choose the theory or choose the data, choose the evidence to support your theory or ideology. And we're trying to get people to really talk about as much as possible, to be as rigorous as possible. Yeah, yes. And we certainly would love to have your audience to tune in to listen to some of these these episodes. And
That sounds like
we'll see.
fascinating.
We'll see whose episode is better.
Yeah, see who does a better episode on weed.
Right.
That sounds like a really fascinating topic area, and so yeah, I definitely encourage listeners to check out the podcast. That sounds like fun. This episode is brought to you by Super Data Science, our online membership platform for learning data science at any level. Yes, the platform is called Super Data Science. It's the namesake of this very podcast. In the platform, you'll discover all of our 50-plus courses, which together provide over 300 hours of content, with new courses being added on average once per month. All of that and more you get as part of your membership at Super Data Science. So don't hold off. Sign up today at www.superdatascience.com. Secure your membership and take your data science skills to the next level. Cool. So in terms of some specific articles that you've written, that have made a big splash. You recently wrote an article that spells out the differences between statistics and data science. So what is the difference? What is data science and how is it different from stats?
Right. Well, I think I've been asked that question many times, and I've given a lot of thoughts on that, like many of my colleagues. But eventually, I realized there is actually a very simple answer. Very surprising, there's a simple answer. The simple answer I came up with is simply to to tell people that the difference between statistics and data science is like a difference between the physics and the physical sciences, or the difference between sociology and the social sciences, right? And so data science, by now, it has evolved. It's not a single discipline. Data science is a collection of disciplines that's certainly including statistics, computer science, engineer, and operation research. And I would go as far as there's lots of philosophers, work very hard on thinking about what makes possible to predict the future, right? All these kind of influential questions. And so at this, I think thinking data science as a collection of disciplines actually is not only important to understand its scope, it actually has real consequences for university for building various kind of data science related enterprise. So in my first editorial for Harvard Data Science Review, again, it's entirely free. I encourage people to read it. I wrote basically say data science is an ecosystem, right? I call it it's an artificial ecosystem. Artificial both in the sense of artificial intelligence because it's computer based, but there's also a sense of how it's related to the whole artificial intelligence. And the real consequence here is I wrote there, and I think many of my colleagues and increasingly more people agree with me, that we should not encourage a university to put together a data science department because that's a too small unit. And it's actually make it very hard to have a reasonable curriculum to cover all these topics. You just get students, way too many things. It's just, imagine you have, you probably never heard of, unless you're from some very small colleges, they don't have enough resources. Rarely any university have a department of science because you just don't know what to do, right? Because science has biological science, physical science, all sorts of stuff, right? So you basically, the universities should build, if they want to build, is like a schools. For example, Berkeley is building a college, or MIT built a college of computing, right? There's various different names, but so you really should think about these are high level. So that's essentially how we, at least at the HDSR, the Harvard Data Science Review, how do we think about data science? And it really gave me the.
In your view, then, instead of creating a department of data science at a university, there could be a faculty of data science.
Absolutely.
Right.
Yeah. It's a very much. What's interesting is that if you think about, and this is not just my view. Michael Jordan, as I'm sure you know him, that from Berkeley, who's a leading true data scientist, both the computer science and the statistician, have been talking about the very similar things. Like he talked about the essentially, what has been such a good opportunity in the last 50, 100 years in terms of for university build new kinds of schools, right? We have School of Science, with School of Social Science, public health, business school. Where is the opportunity? What has been a topic so universal and important that worthwhile to have a new school? And so data science is one of these very, very, very few opportunities. And there's lots of challenges, and including where exactly or what exactly should be in a data science, schools or faculty. But I think the general scope is quite clear. It goes beyond a single discipline.
Right. That makes a lot of sense. Cool. All right. So yeah, so data science is a big umbrella that includes
Exactly.
statistics, computer science, philosophy, lots of other disciplines. Now, in that same article, you also talk about two concepts that I hadn't heard of before. So maybe you can elaborate on them for us. Not data mining, but data minding. What's data minding, Xiao-Li?
You haven't heard of. I don't blame you, because I coined that term, and I hope that a lot more people will think about that. Well, let me say that the what I have in mind, and that's what I wrote that article about, is that I want to really emphasize that how important the issue of data quality is, particularly these days when we rely on massive amount of data and a lot of algorithms, including deep learning, or maybe particularly deep learning, that we don't quite understand how they work. I know we
Right.
have been working very hard. Various researchers has been really making big progress to understand those things. But we rely on those massive amount of data and these really interesting algorithms to come up with these solutions that as you probably can tell, that people used to say what they call garbage in and the garbage out, right? Because if you have very low data quality, particularly you use these algorithms to learn the pattern from the data, and you may get something is really quite bad. And in this particular article, I said I'm not worried about a garbage in, garbage out, because if we recognize they are garbage, we know how to deal with them. I'm more worried about garbage in and the package out, because things get
Mm,
packaged very nicely. People just take that, take that as it is. And
mm,
the example I used, and that's what I meant by data mining. Data mining basically said we need to do a very serious, before you do the data mining, that you should really think through the data quality, understand where data came from, who collected data, for what purpose, how the data were measured, what question was asked, and how that were processed, and really minding the data, right? Thinking through all these questions, and do a serious kind of introspection of the data quality. And I always use the example, which I think most people understand. And the 2016 election predictions, we in the end all get a surprise, regardless your ideology, is just because we had so much data, so many predictions, all went one direction, right? Most of them. And that was
mhm.
clearly there's a data quality issues, right? Because
Right.
clearly there were, I did some studies in 2018 to show how a seemingly tiny what they call non-response bias, the idea people did not want to tell you what they really think. Not necessarily they're lying; they just say, "Oh, I have not made up my mind," even when they have. And so that kind of issues that if you don't understand it directly based on the data using traditional methods to analyze, you get tons of these predictions all go one direction, and then we collectively gets very frustrated, right? And so I well, let me give you a specific example
Sure.
about the kind of data mining that I did in that particular article, which I think was a very telling example, and it shows the importance of doing that. I wrote that article because I was asked to by this journal. This is a journal of Royal Statistical Society from England.
Mhm.
They had a collection of articles on kind of data science, and they asked me to
Yeah.
write an editorial. And
Yeah.
they
Do you know Martin
Go ahead.
Goodson? I think he leads that section.
I think so,
Martin
because there's
Goodson is the one who leads
there,
the data science section at the Royal Society.
oh, you're
Um,
talking about Royal Society. I'm talking about the Royal Statistical Society. Yes, there's another. Okay.
yeah.
Yeah, but the Royal Society also have been doing a lot of great stuff there. But I was asked to write, writing some commentaries in a collection of articles, and they want me to write something like the Harvard Data Science Review kind of editorial. I told them like, be careful what you wish for, and because I said I'm going to be very critical. So I went through every article, right? Yeah, keeping in mind in terms of the data quality issue. So I basically for every the article again is online, so if people want to welcome to read it. I basically look through every article to to see how they talk about the data quality issue. Every article talk a lot about data analysis, all kinds of fancy stuff. But I say, wait, I want to see how you talk about the data quality issue, right? Before you do all those things, because I know how those things will affect your results. So here's one very simple example. One article wants to study these heat warning system, like when summer is coming and when temperature keep getting high or you get forecast there's going to be a heat wave for a few days, should the city to issue a warning, particularly for the elderly, for the more vulnerable population. And this group of people, they want to study as well. In the past, they don't know how these decisions were made. They said, let's look at the data, right? Let's look at data to see if these warning systems actually make a difference, right? So they pick up a city, I think it was city, Montreal, that in Canada, that they want to study, like, they look at the 20, 30 years of data, trying to study whenever there's a heat wave warning, how does that affect the deaths happen in the city, right?
Right.
So it was actually really quite a serious study, but there was one problem. The problem is they used the city data, and they say the data, there was just one sentence. The data was the data they use is whatever the city recorded, like how many deaths on the day. Okay, so they use the data. Now I happen to used to study a little bit of issue about reporting delay for the city to record these data. So I had a very simple question, right? I had a question is like, when they say these deaths on say today, are these deaths happen today or they get recorded today, right?
Right.
That makes a big difference. Particularly, for example, CDC's data on the vaccination, they have on average about a 5 days delay, right?
Right.
Now, 5 days is enough to dislocate the heat wave and the real deaths, right? So it's just a simple question, right? Because you would know that if the 5 day differences, you will see a lot less correlation compared to if the deaths really happen on that day. But apparently that question was never asked because I did not find anywhere in the article talk about that. I don't know if the review remind them, but for me, like these are kind of questions that anybody serious about the data analysis should ask. It could be a simple question to check with the city. You may find out there was actually delayed. Now then the problem become more complicated. How do you adjust for the, say, 5 day, whatever? It probably will have another distribution. Right. And that's a kind of question that I think a data mining should do. Otherwise, you will be analyzing data, miss the real signal. So that's just a simple example.
Data mining. Yeah, that makes a lot of sense. And it's a general concept to understand your data before you start data mining or modeling. Definitely critical. It is way too easy today to take whatever data you can find, throw it into a model, and then, as you describe, have garbage in and then supposedly something well packaged coming out the other end. All right, so data mining was one of the terms that you introduced to me in that article. Another one was a data confession. What is that?
Yes. Well, that is basically, I'm encouraged that anyone, particularly those of us who are scholars, publish any data science articles, we should tell as much as possible the data defect, especially if we collect the data. We tend to not confess that much. Not necessarily people want to hide things, but people, the journals probably have not required that much to tell people, like, you disclose, right? Disclose, like, anytime any of us have done the real data science project, you know how messy data are. And from the, conceive the questions, how to collect the data, there's lots of judgment being made. And the process itself sometimes is completely get lost, even if we're the one collecting the data. So by data confession, I really wanted people to think through and also record during the process. How did you come up with these ideas? Where did you come to the data? What corners you have cut? we all have cut corners, right? And it's a massive process. But we know whenever we send the papers to publish, typically, and this has been a kind of a tradition in the field, right? We spend a way more time talking about the algorithm, the models we fit,
Right.
everything we do. We say a lot less about the data itself, and particularly
Right.
when the data we got from somewhere else, right? And now it's even harder when we got it somewhere else. Like we don't even know what else people have done. So I'm encouraging general culture, which this is not really new. This is this is I was inspired by talking to people from library science, on my board of Harvard Data Science Review, because they're the one worried about data curations, right? Just like library, like create books, because they're the one thinking about how the data is, which versions, how do you record the whole thing, right? There's, how do you think about talking about reproducibility, replicabilities? Like, how do you make sure that future others can verify what you have done if you didn't report all those things? So these are hard. These things are much more tedious and often kind of not much get rewarded, because the more you disclose, the more the review comes back say, hey, your study really does not worth that much. You should do better, right? So you can see the incentive system is not quite right for people to confess. And so that's why I'm using this phrase, data confession. I think if we really take a data science seriously, take about replicability of science, reproducibility of science seriously, more of us should really do more about, disclose all the defects, the warnings for others, right? I'm not saying we cannot proceed, but I'm just saying it's much better for us to all tell people what are limitations, what are the things that, we all do the best we can, right? That's how the science progress. But we should try to do as much as possible. I know they're sometimes very hard, particularly there's data confidentialities, all kinds of issues. That's another big topic by itself. But I think I'm just looking at all these articles in the published, at least in statistical literature. I think we disproportionately spend way too much time on the later part, which is absolutely important. But there are this much more fundamental to the early part, which we tend to say much less of sweep under the rug, so to speak.
Nice. Okay, understood. Yeah, that does. Data confessions do sound like another key part of helping data science with reproducibility. And again, it's kind of related in a way to the data mining,
Yes.
because we're concerned about the data quality going into whatever models we develop. And as you say, we put outsized attention on model development and not enough on data quality. So in a separate article, actually, no, this one's a YouTube video. So we'll be sure to include links to all these. So the article where you talked about differences between statistics and data science, as well as data mining, data confession, will include a link in the show notes to that article, as well as to
Thank you.
this video on another concept related to kind of a data science philosophy, just like differences between stats and data science and data mining and so on. So you can see that there is not only a lot of philosophers working for the Harvard Data Science Review, but also a lot of philosophy going on in your head, Xiao-Li. So this one that you mentioned in this video was that you claim that there's no free lunch in data science and that data come with trade-offs. So what does that mean? What are the trade-offs that data scientists must be aware of when they work with data?
Sure. Thank you. Well, first, I want to say this no free lunch is not just a principle for data science, it's a principle for life, right? I mean, we all like to get, things are clean and cheap and, the great, but, you know how in life that you usually have to make a compromise. We all like all the best stuff, but then, things comes with a price. And the particular examples I have in the data science space in terms of trade-off, there are really multiple of them. One of them probably these days gets a lot of attention is the trade-off between the data privacy and the data utility. And the particular example, and for which Harvard Data Science Review will publish a special issues on the defense of privacy for 2020 census, right? Here is a trade-off, or rather, a dilemma that the Census Bureau was given, right? The Constitution mandates every 10 years, Census Bureau should collect the data, as accurate as possible, right? Then you also have, Title 13 says that you need to protect people's privacy as much as possible. Now, it'd be wonderful if there's a way to have incredibly accurate data, but it's also private. Now, that's not possible. And I always tell people, like, if you think about the term
Right.
data privacy itself, it's bluntly, it's an oxymoron term, right? Because data
Right.
are born to reveal, and
Right.
privacy means to conceal, right? So
Right.
that we are just forever having this problem. And I also said that we humans are very good at creating, dilemmas for ourselves, right? We as humans, we all have lots more information. We like having information about others. We like have all the information help us to build AI systems. And but then it was no. You collect information on others, but don't collect them on me, right? And now the problem I always say, the problem is other people are us. There's just no way to get around it. So you can see that is one big trade-off. The other is the trade-off is we already touched on the data quality issue, right? It's a trade-off between data quality and the data quantity. And now, in the ideal world, you say, well, why there should be a trade-off? Should have lots of data with high quality. Well, great. And sometimes that happens. When that happens, congratulations, you have a much easier job. But often it's the case that you can get a massive amount of data, for example, from social media, right? Facebook, other places. But these data comes with really questionable quality issues, right? I very recently published an article in Nature, looking to the Facebook's survey and other surveys on these vaccination, uptake, right? And then it turned out to be they're quite biased, and we all understand why, because people on Facebook tend to be have a higher education level, for example, compared to people are not on it. So when you do survey there, you end up seeing the vaccination rate is much higher. To a point, at some point was 17% points higher than the CDC benchmark, right? So there. On the other hand, you can have a very good quality data if you have a very well controlled study, so on and so forth. But they tend to be much smaller. They're much harder to conduct, much more expensive. So you have this trade-off between data quality and the data quantity. Another trade-off is between what I call the data cleanness and the data validity. Any data scientist, yourself included, I'm sure that that we spend most of time trying to clean up the data when we do anything, right? The data comes messy, things are missing, things that do not match, I don't know how this thing was coded. And we all wish the data is very clean. Now, occasionally we will get a very clean data. Then I would be very worried, right? Because I know that there's lots of cleanup done to the data. And I need to know how those things were done. And often you will find out it's very simplistic thing, have done to it, right? So that's another trade-off, that you can have very clean data, seems very easy to analyze, but you may get the answers that really are not that relevant because someone else have trying to clean up the data. One very common approach, unfortunately still happens, is for example, called a complete case analysis, right? People will throw away any cases where there's missing data. Only study these cases where everything's completely recorded. Well, it is very easy to analyze, but that everything gets recorded. This probably is a very special group of people, particularly for example, when you study health issues. Whose record is completely recorded, right?
It's not
get a very
random sample.
It's not random represented sample at all. Right? So these are a tons of these trade-offs, and all these things is what I meant by there's no free lunch. Now, the upshot of that, the good news is there's always tons of jobs for good data scientists or statisticians because of these issues.
Right. Yeah, these are not issues that it will be easy to automate away. So people sometimes people are worried about, AutoML is going to take data scientists' jobs, and it's precisely because of these issues. This AutoML approach where we figure out what the optimal algorithm is and its hyperparameters. Okay, aspects of that in some circumstances can be automated, but
definitely
it's not useful if you have a high quantity of data with low quality, to use one of your comparisons,
Yeah.
or you have so much pre-processing happening, the data are so cleaned up in some automated way that the data are no longer valid in the real world. They're becoming irrelevant.
At least not right. At least not answer that relevant question that
Right.
you really care about. I mean, issues like talking about I'm all for to automate as much as possible, but we have to be really reasonable in terms of understand this what I call the no free lunch principle here, right? The example I just give on this heat wave studies, it would be so hard to teach any machine to recognize, say, hey, did you check this data? Is really the death happen on the day, or that was a death report on the day? I mean, how would any algorithm do that, right? The only reason I can do it is because I have done studies in some other cases before. I have this way of thinking about those things. Now, I'm hoping some days that we may be able to train the AIs to be able to think like a human, right? Not talking about real AI, to accumulate from past experience, but we're far from there yet. And and I'm not quite even sure we can ever get that, because it's a kind of a thinking, connecting dots is just not takes the human intelligence that and most time we don't even understand how human intelligence works itself. So
Right.
it's hard to model it, right?
Yeah.
But that's the kind of experience comes with the humans that it's very hard to automate.
So cool, Xiao-Li, to hear so many data science philosophy thoughts from you. I've really enjoyed this episode so far, and we've got more to come. So another one here from another article of yours. This is from an article in the Harvard Gazette, and you were talking about this paradox related to having large amounts of data. So, we've talked already a bit about quality versus quantity, so maybe this is going to relate again here. But in this Harvard Gazette article, there were elements related to COVID-19 and the paradox of having lots of data. And then you also have a paper where this can happen with electoral surveys. So can you elaborate for us on how bias is amplified the larger the data set we have?
Yes. Well, thank you very much for asking the question. And in fact, the Gazette article was really about the one I already mentioned, the publication in the Nature on this COVID vaccinations. But let me backtrack a little bit because that's where I started, and I surprised myself after I'd done the calculation. This was, I think, the other in terms of electoral one is the 2018 article. What I did was I tried to quantify the data quality. Now, it's much easier to quantify data quantity, obviously,
right,
but it's much harder to quantify data quality. So I started this work actually really back in 2012, 2013. The department at the time had a visit, coming from U.S. Census Bureau by name Jeremy Wu. And Dr. Jeremy Wu at that time made a presentation to my department, and he asked the following question, which I think is a really fun question for all the audience to think about. And if I have chance, I usually will question the audience, how would you answer that question? So at the time, and particularly now, there's a lot more of these cases that U.S. Census Bureau was thinking about, how do we utilize all these administrative data, right? There's lots of data are already there. And the question is, how do we use these data that we know they cover large percentage of a population, but they were not collected for statistical inference purpose. So they are not like a randomized, they're not a probability sample, right? So Jeremy asked the question to me and my fellow statisticians, like, if you're given a 5% data of a population, which we tell you that is a good quality, statistically valid in a random sample, versus 80% of the population data, which I just tell you it covers 80%, but I have no idea the quality of the data. Which one would you trust? Do you trust that 5% of the data, or you trust the 80% of the data, right? Of course, a statistician's first response would be, or should be anybody respond, would be trust for what purpose, right? Jeremy responds saying, well, let's say we want to estimate the population average. For example, we want to estimate in the end how many people will vote for a particular candidate, right? So, most statisticians, the answer will be, I'd be trusting that 5% of the answer, because 5% of the data, because I know how to assess its uncertainty. I have all the formulas because it's a random sample, right? So Jeremy said, okay, that's fine, okay. But now I'm going to change the question. You still have the 5% of the probability sample, but the other one covers 90%. Do you change your mind? Now it's 90% versus 5%. 90% means I know it's covered 90% of the population, but I don't know its quality.
Right.
Well, some statisticians, myself included, start thinking, well, maybe 90% I probably should have switched. And there's people, some people still don't switch. Then Jeremy said, what about 95%? Right? At some point, he will say, wait, I had to switch because by the time I get 100%, assume people answer responsibly, everything, 100% should be the right answer. Yeah. But that got me thinking. The Jeremy's question is, how do you measure the quality, of your data? Like, where do you do that switch? What's the calculation here? And that's a fascinating question, right? So that's how I started to do this work. And I eventually took years, actually. Eventually, this article published in 2018. And I did the following calculation, which was kind of mind-boggling, which really started my kind of journey about pushing people to think about the data quality issues. So I did the following calculation using 2016 data. I can estimate in 2016 data how correlated people's response to say whether they vote for Trump or not, and their willingness to participate in a survey. Okay, so the idea is that correlation should be zero if people just answer honestly, because it shouldn't be that, say, you look and say, because I'm going to vote for Trump, therefore I don't want to tell you. That creates bias, right? So we estimated, because after 2016 we know the answer. So we estimated what was that correlation. The correlation turned out to be minus 0.5%. Okay, it seems very tiny, minus 0.5%. Minus because the answer people tend to not respond are the ones who want to vote for Trump. So it's a negative sign.
Right.
It turned out that a minus 0.5% essentially caused a tremendous loss of effective data size. By which I mean the following. Well, I did a rough calculation. Before the election, there were so many surveys out there. I did a rough calculation. It's amounts to, we had about 1% of the voting population, eligible voting population, provide their opinion. Let's say that's 2.3 million people. That's about 2,300 surveys, each with 1,000 people. But if I do the calculation, what's the effective sample size? Meaning, like, the statistical information in that 2.3 million answer, which sounds a lot. What's the equivalent answer if they did not have any defect? It's like coming from a true, simple, random sample. The answer is a surprising one. The answer, this is publishing the article, is about 400 people, right? So basically, the 0.5% negative correlation caused a damage, which essentially lost about 99% of the data. Like the statistical accuracy.
99%.
Right. The statistical accuracy, we can show mathematically, is equivalent to you have the same answer from like 400 people without that bias. Okay. Right. So that was the calculation. And so I carried the same calculation for that COVID, a study done by the Facebook. And what we did a calculation is they have 250,000 people, but in the end, that because the correlations they have, that compared to the CDC, the benchmark, their sample size is essentially anywhere from like 10 to 250, compared to 250,000. So that's kind of a thing what I call the big data paradox, because it comes with two parts. Not only you have a tremendous reduction of the sample size, because you have so much data, and if you did not realize how small the data size is, if you just do the traditional confidence interval calculation, right? Because you want to give error bars. Your error bar will be way too small, right? Because you use this erroneous sample size. So your error bar is so small, you will actually, the more data you have, the more you'll be centered at the wrong place. You will make sure yourself you never get to the right place, right? This is what I meant by the big data paradox.
Right.
Because the larger the data size, the more sure your answer is, but you're centered at the wrong place. Your confidence interval literally shrinks and the sample size goes up. You actually you have a higher and higher chance to prevent yourself to get to the right place at all. That's the big data paradox.
This is something I think about a lot as we have lots of data. And so this is something that impacts me all the time. If you try to use statistics statistical approaches, like frequentist statistical approaches that were developed over 100 years ago.
Yeah.
So, the common way to get those error bars would be to say divide by the square root of the number of samples you have.
Exactly.
And when you're dealing with millions of data points, that means that your error bars they don't exist.
Right.
You're saying, I
Right.
know exactly where we
Exactly.
are.
Right.
Yeah.
But yes, you know exactly where you are, except you're at the wrong place.
Right.
So the whole paper I wrote is to really show these calculations. And speaking with these frequentist methods, they're based on a fundamental assumption, which is that the data are well mixed. It's a
Right.
probabilistic sample, right? And
Right.
and so that's where
Right. So
and
we're taking techniques where we explicitly say, and even if you're in an introductory statistics class as an undergraduate student, you're saying, okay, this statistic, it only applies if you have a representative random sample. But then we're constantly using that today in situations where we don't have a representative random sample.
Right,
And
we know we
pretending that
don't
we're doing
have it.
Yeah.
Right, because and the thing, I guess, in my 2018 article, it's also available online. I think the surprising part, even some of my statistical colleagues are still debating with me. What my calculations show is what matters is no longer just the sample size, is the relative sample size, how the sample size divides by the population size, and the larger the population, the worse you will end up with. And that's to a layperson, that's not surprising, right? The large population is harder to analyze. But the statistically, I was using the following analogy to help the general population to understand why the statisticians at the very beginning say we can ignore the population size, right? It's very much like when you taste a soup. If you're tasting soup, if you have a well mixed soup, right, regardless the size of the container, all you need is just a couple of spoons, right? Because you can taste how salty it is, how delicious it is. As long as the soup is well mixed, you don't really need that much. But if the soup is not well mixed, then you can see the size of the container really matters, right? Because the larger the container, the more chances there's some salty chunks are somewhere else, right? And so once you lost this kind of a well mixed assumption, that's essentially is what it is. It's a well representativeness, the homogeneity. Then the problem becomes a lot harder. And the problem these days is the social media data, particularly is because of self-operating data, right? You cannot really randomize people. Say you go on this Twitter, you go on this Facebook. You don't. That doesn't happen. Right? You lost the control in terms of statistical kind of a control, and so then you really have to be careful. We all knew these things, but we all hope these problems are not that big. But what I did was just to show how seriously the problem is, because it really kills 99% even over the amount of data, and you can just do this mathematics. It's just out there.
Fascinating. That was a really great explanation of this paradox of having more data. Really enjoyed that discussion. And it leads perfectly into our next topic because we started talking about frequentists. And so yet another article you have, it's an amusing article in a generally amusing column that you have in the Institute of Mathematical Statistics Bulletin. So you have a column called The Excel Files, which I can only assume is a play on the X-Files TV show name and your name, Xiao-Li. The
Correct
Excel
inference.
Files. So amongst many fun articles in there, there's one of them titled BFF Forever. And so BFFs, for those of us who aren't high school aged girls, stands for best friends forever, BFFs. And you use that to summarize the three big schools of statistical inference. So frequentist is one that we just talked about. Another one is Bayesian. And the third one is actually one that I am not very familiar with, Fiducial. So for our listeners' sake, Could we go over what these three different schools are, Frequentist, Bayesian, and Fiducial? And in the last case there, you're going to be explaining it to me for the first time too.
Yeah, well, I don't blame you. Fiducial is one of these perspective has existed for a long time, and essentially coming from R. Fisher. Fisher has contributed a lot to statistics, as you know,
Yeah, to
and
Frequentist.
but it's also has always been regarded as the Fisher's biggest blunder because it's the most controversial one. So let me give a try. Okay, this is self-worth. We can do an episode for 2 hours to explain all these three different perspectives and why we have this kind of a community called BFF. First, I think the frequentist one probably is the one that most of us learn statistics. That's where you start from, right? And I'm sure because the most textbooks teach that, and I certainly think I went through the whole process myself without even knowing there are these different names, right? So I think the best way I can explain this, let me really give it a try. That start from think about data, all right? So data essentially have two pieces in any data. Well, one part is what we call a signal. That's the pattern. That's something we want to understand, to know. The other part is noise. These are part, they're there. It's annoying. We want to get rid of them. But data basically comes with both the signal and the noise. And so for the entire data science community, in fact, all we do is trying to separate what is signal, what is noise. The complication there is, first, how do you do that? Second is, signal in one study is noise in another study, and vice versa. Because the notion itself is a relative one. So you can see why the philosophy is there all the time, okay? Because, these issues, for example, particular one, I also done quite a bit of study is on these, individualized medicine, right? There is, what's a signal, what's a noise, what's evidence. It's just very complicated. But let me go back to explain these different three different schools. The frequentists essentially focus on data itself. They every study, whatever study you do, right, you need to think about what is a replication. Because if you have any problem, in order for you to convince anybody, particularly scientifically, you need to talk about like, if I do this study again, like my method will work, not just for this one case. It's not even clear what do you mean by say working with this one case. You have to think about replications, what the replications are. And it is in thinking these different replications, these different philosophy comes in. The frequentist thinking is focusing on data. Basically thinking about, hypothetically thinking about that if I can repeat the process again and again, seeing different data, how my procedure is going to work. For example, in the predictions, right? We're basically thinking about, well, the whole randomization say you only have one sample. Let's say we talk about 400 people. But the idea here is that if I do this replicate the 400 people again and again, many times, how my procedure is going to work, right? So that's called a frequentist. So you see, it basically requires you think about the data you actually don't have. That's the frequentist one. The Bayes said, well, I don't care the data I don't have. I care about the data I have. Can you tell me, like, based on the data I have, what's going on? Like, how do I make an inference problem? Because all I have is my data. Now, the problem here is that if you think like a frequentist there, you will get stuck because there's no replication there, right? Data are fixed. And whatever the scenario I want to know is a fixed scenario. Now, hypothetically, it's unknown, right? So the Bayes will think about, okay, now let's hypothetically think about all the different scenarios that could have generated the data I have seen. Among all these scenarios, which one is most likely?
Right.
Right? So, it's essentially, for example, if you have some COVID symptoms, now I have to think about there are many possible ways why you're coughing, like what I'm having now, right? There are many possible ways you were coughing, right? And which one is most likely? Now, I think for most people, that is a question people want to really have the answer. I don't care about, other people's symptoms. But in order to answer that question, you need to come up with a replication. Think about all these different scenarios. So that's what the Bayesian called the prior knowledge. You need to think about, and that itself is a controversial notion. You need to think about probabilistically what are all these different scenarios you could have. And a frequentist can reject the notion and say, no, I only have one disease. Okay, I don't want to assume that I have a multiple disease. So, but you see the direction is different. The replication is now, imagine all these different scenarios could have generated exact data as I have. Okay, so that's the one is, so I always have these fan shapes. One is thinking about one scenario generate all the different data. The other is a reverse the shape. Think about your data, but all different scenario can generate the data as you see. The fiducial is the hardest one because fiducial does not fix either one of them. Fiducial is essentially thinking about the pair. Think about all the data, all these scenarios you can have. Imagine, every person in the population, you have your symptoms, you could have your diseases, okay, and you have all these different pairs. So fiducial, instead of working on the frequentist working on the data, the Bayes working on the signal. They put a distribution on the signal. And the frequentist working with the noise part. Frequentists look at the difference between the signal and the data, thinking about what are the possible noises are consistent with the symptoms I'm having. And it operates on this kind of a joint space. And it itself has philosophically and even operationally, have quite a bit of trouble. That's why you probably have not heard about, people don't really teach that much about. But it offers a way, what the frequency is trying to achieve, what the fiduciary trying to achieve, is they're trying to answer the base question, which is giving my data, what is the disease I have? But they don't want to assume that kind of a prior knowledge, which you may or may not have.
I see.
So that's why I make it very harder. They're trying to use a distribution on the noise to infer that distribution on your disease without assuming the prior distribution. And it end up, that's not really possible, but there are certain scenarios under which that you can get pretty far. And that's why the school itself is a much more philosophical and much harder to operate, much harder to teach, much harder for me to explain. And I'm sure all my fiduciary friends will say, Xiao-Li, you didn't give the right interpretation of the explanation. But I tried. Okay. I would invite anyone trying to explaining fiduciary without formulas.
There's no way for me to know if it was the right explanation, but it did make sense to me. So I like that. Fiduciary statistics, it makes use of the data that you have. It doesn't worry about some unknown distribution that you don't have. And it's trying to make inferences without priors that Bayesian statistics relies on.
Right. It's trying to give a distributional answer without assuming a prior. And it turned out that you can do it in some sense because you do have this distribution on the noise. So the way they do it is essentially saying, just imagine very simply, your data is noise plus signal. But if you have data, once you see the data, if I have a distribution on the noise, it somehow implies that there's distribution on the signal, right? Because the data equal to the signal plus noise, I can kind of solve that equation. But except that solving these distributions is not exactly right. So that's why the complication comes in. But there is an attempt trying to do the best in terms of the best of the both schools, and that's why the thing is still alive. And in fact, what's interesting that there are increasingly more people in the machine learning content. They're doing things that they don't realize they're actually doing fiducial. They're plugging this thing, solving equations, assuming this is known, that known. If you look at them, they're not coherent. They don't follow probabilistic rules. They follow some solving equation rules. That actually is what the fiducial does, except that most people don't know what they're doing is actually a fiducial answer.
Yeah, interesting. You learn something new every day. That's a big one for me. I love that I've learned a whole other school of thinking on statistical inference, fiduciary. And so we've never had, obviously, an episode on fiduciary statistics on the Super Data Science Show, or I would know what it is. But if listeners are interested in hearing more about Bayesian statistics, we have an epic 2-hour-long episode number 507 with Rob Trangucci from last year, from 2021, that is all about Bayesian statistics. And I thought we might be taking a risk with that episode and that it would be too technical, but it's one of the most popular episodes we've ever had. So you can check that out if you're interested in learning more about Bayesian stats. But my question for you, Xiao-Li, is, okay, given now that we're aware of these three schools of statistical inference, Bayesian, Fiducial, and Frequentist, there's a lot of people who debate that one is better than the other, but you think that these three, B, F, and F, Bayesian, Fiduciary, and Frequentist, should be BFFs forever. They should be best friends forever. So why do you say that?
Well, it's a great question, and the reason I say that, and also my BFF, community colleagues, is because we all kind of went through these different perspectives. We try to convince ourselves which one is the best. We end up realizing we really need all of them because each one of them have something to offer, and each one of them has its own weakness. And in fact, I come to a conclusion. This is part of saying I'm trying to do this more foundational thinking, that I don't think we will ever settle which one is better, because fundamentally, anytime you do anything about data science, right, there is a leap of faith involved. But let me explain what what that means. This is part of the reason why single philosophy is so important for thinking about the data science itself. But you have to ask yourself, anytime I have the data, and I'm asked to use the data to predict something which nobody knows for sure, because if they do, then we don't need to do the prediction. What makes possible to go from the data to whatever this thing I want to know, right? Logically, why would that be even possible? What's the part of nature, or if you believe God, which part of the God that allows us to do that, right? So basically, the every school, and that's why lots of philosophy involved, is thinking about what are the links between what we know and what we don't know, right? And in this process, that these different approach, the perspective I just talked about, is all trying to use the mathematics to help us to make the link, to make that connection, right? And I can tell you what's a problem with each one of them, and why I'm in the end, and I think increasingly more people realize we should use all of them. First, we started as a frequentist, like myself, right? But eventually, the Bayesian convinced me that the frequentist has one fundamental flaw, which is that, yes, you can study all these beautiful answers, tell me on average something works. But in the end, right, even you tell me that medication has 95% chance work for you, right? Well, there's still 5% chance that it doesn't work for me. And the 5% in the population is a huge amount of people, right? And how do I know I'm not the 5%? Like, how do we know this average answer is relevant to me? So the frequentist one forever suffer this could be completely irrelevant, right? Just for me. So then we go to the Bayesian answer. The Bayesian answer is obviously, well, it will be very relevant for you, okay? Because that's how it is set up. But the problem is you need to make lots of assumptions in order to get an answer. The question is, how do I know these assumptions themselves are reliable, right? Now, there is a school called objective Bayes. The idea is, can I use a prior knowledge, which people call a non-informative prior? Can I assume, basically say, I'm very ignorant and use that school? Now, if that can happen, that'd be wonderful. But it turns out, this is the fatal thing about the Bayesian statistics. Bayesian statistics, there's no way you can put down a prior which is truly ignorant. Probability distribution does not allow you to model ignorance. Because anytime you put down a distribution, people say, well, let's assume like everybody equal chance. No, equal chance is not being uniform, not being ignorant. Equal chance is a huge amount of information, right? Anytime you put down a distribution, it will ask you to specify the relevant frequency of two different states, right? So you have to do that. So it turned out the problem with Bayes, I've been using this phrase, because thinking about doing mathematics without the concept of zero. Because in Bayes, there's no zero information. You always have to assume something, right? So that's where now I start moving to the Fiducial, because Fiducial said we want to do the inference, but without making any assumptions, without a prior, essentially like the zero information, and they can do that. But it turned out that because the zero requirement, it turned out that how do you operate? How do you, using in the Fiducial framework, or more generally, there is a whole area called imprecise probability. The imprecise probability is exactly trying to address the issue the probability itself is too precise because the probability itself still need to specify the relevant frequency. Sometimes I just know the answer between 3 and 5, but don't ask me like how likely is 4 compared to 2.5. I don't know. I know the answer between 3 and 5. How do you model that? And that one, current Bayes probability cannot handle that. So the imprecise probability is trying to handle that kind of thing. But it turned out that I just wrote another article recently. When you do that, you still have to make a judgment how you want to update the information. Like in Bayes framework, you have a Bayes zero to tell you how to update the information, right? There's a clear rule. But broadly, when it goes to this imprecise probability, you have a variety of different rules. It depends on whether you're an optimistic person or you're pessimistic or you're opportunist. Like these different perspectives will give you different rules, give you different answers. So then I realized, okay, now see, every school has problems, right? Every school, either you get answers not that relevant, or you need to make lots of assumptions, or you still need to make some judgment. So the thing in the end, you realize that all schools, they're all trying to do the right thing, but they all come up with different answers, and not because they have defect just for the sake of having defect. It's because if you think of fundamentally what makes possible to make prediction of the future, I think that there's just a fundamental problem is there's no simple answer here. And that in the end, just like the whole data science itself, we basically have to use whatever the methodologies, all can help. But we need to be aware of the limitation of each one of them, and we understand where you're going to suffer if you use it in not in the right way. That's why I think we should all use all of them.
Beautifully said, Xiao-Li. That was an extraordinary section of not just this podcast, but of any of the episodes we've had. That explanation of the differences between frequentism, Bayesianism, and fiduciary approaches, and that timeline that I think a lot of us go through. So I'm maybe early on in my Bayesian phase. And I look forward to exploring it deeply enough that I see that fiduciary is the right thing for some circumstances, but yet not all.
It has holes. It has holes itself. Yeah.
Very cool. All right, Xiao-Li. So this has been an exceptional episode, and I'm sad to say that we're starting to get near the end, which means that it's time for me to ask you for a book recommendation.
Absolutely. And I'm going to show you which book I'm reading, and it's called Beyond Flavor.
Oh, yeah.
It's a book by Nick Jackson, who is a master of wine. And this book teaches you how to do blind tasting. And now you may ask, why a statistician is reading a book on blind tasting about wine? Well, first,
I know you like wine. Yeah.
I love wine.
Yeah.
And the second, I think that if you truly understand how to, judge the quality of a wine and how nuanced the process is, you would understand the data science far better than people don't go through that process. The reason I'm saying that is that for any ones we ever have any experience with the wines, wine just comes with so many different features, right? And the predictive wine is like, and it's also very personal. The people, the wine looks like it tastes maybe fantastic for you, for somebody else, they say, that's terrible, right? And this particular book was recommended to me by a former student of mine who's working with me on data privacy issue, and her name is Robin Gong, a faculty at the Rutgers University. She recommended that book to me because she knows I love the wine, but also we talk about this whole issue of how to predict the wine quality. Here, let me be very specific here. Why this is a terrific book? Because why it's called Beyond Flavor? Because most people taste the wine trying to guess which wine they use the flavor. They say, well, how does it taste? And Nick Jackson basically said, well, it turned out that the flavor is not a good predictor. Okay. Because particularly in these in these kind of blind tasting, particularly if you want trying to pass these exams, like they give you these much more tricky ones, right? The flavors are kind of similar, right? And so you need to look for the structure of the wine. For example, he talk about the acidity of the wine, And basically, this is like for those people who learn do machine learning. You're basically like you're doing feature engineer, right? Engineer. You want to see
Right.
which is a good good predictor. So he
Yeah.
particularly talk about that when we think about the acidity, we just say, well, that the level of the acidity, and he said, no, that's not enough. You need to think about the level of acidity, think about the type of acidity, but also the shape of the acidity. And I say, I never heard of what is the shape of the acidity. Well, and he talked about like how when you drink the wine, when you sip the wine, where does the acidity start to grow? Does it always flat all the way? Or started kind of strong, then goes down, or started low levels, then it goes up. And he said in different wines had that kind of different shape. If you understand that shape, you can do much better predicting a blind wine. So this is essentially machine learning, right? Essentially, it's like a human, way trying to recognizing these patterns, right? So I would certainly highly recommend the book, even you don't care about the blind testing. But I think there's lots of thoughts there in terms of these kind of a very practical way of engineering the features and for these predictions. And I want to say that if we can ever teach machine to really do what blind wine testing, now we're talking about real artificial intelligence. And I always think about someone, maybe you should start something called a deep wine. So if you can do that, and then we're really thinking about how we think like a human, how the machine can think like a human, and to do this incredible hard, prediction.
Nice. All right. That is a really fun recommendation. I also didn't know about acidity shape. That sounds like quite an interesting feature for our deep wine algorithm that no doubt our listeners are now going out and building to realize AGI very simply. That's all it took.
That's all it took, yes.
Fantastic. Xiao-Li, thank you so much for being on the show. No doubt our listeners learned a ton from you. How can they keep up with your latest? Do you post on social media or anything like that? I guess obviously the Harvard Data Science Review is the place.
That's a place to I'm on Twitter. I actually refused to on Twitter for a long time until I become the editor in chief of the Harvard Data Science Review. And people say you really got Twitter because that's a good way to get promote HDSR. So yeah, and I'm on Twitter. I am on. Well, my email is open, so if anyone is interested, feel free to shoot me email. I may or may not be able to always answer, just because I get there's a volume here. But I think HDSR will be a great place to really check out what's the latest in data science. We have these different columns. We have 6 columns on from these kind of recreational to we have. I should share the story with you. How do I come up with the term data mining? Instead of data mining, because we have a column on the history of data science called mining the past. And I was talking to some other co-editors. We were talking about coming up, a column about the future of data science, meaning training the pipelines, talking about K-12 students. And we want to have a title. So I said something like, since we have a mining the past, why don't we have a mining the future? And one of my board members, she misheard. She said, "Oh, I like the minding the future." Then I said, "Oh, that's better than mining the future." That's how we come up with the term. So we have a column called the mining the future. That's where I got the mining, data mining itself. And we have articles from very perspective, kind of philosophical articles, all the way to the very technical ones and education ones, applications, and so it's all free. And if you want to get a hard copy, we have these hard copies to sell, the inaugural volume online, and that's I think it's worth to check out as well.
Very cool. And of course, the Harvard Data Science Review podcast as well for your monthly fix of recreational topics such as recreational marijuana, wondering about the existence of aliens, and so on. Xiao-Li, thank you so much for being on the show, and hopefully we can have you on again in the future someday.
Thank you very much for having me, and this has been really a great conversation, and I hope that your audience will enjoy it, and of course, I hope they will listen to our podcast and also as well check out HDSR. Thanks again.
What an honor to be able to speak with the extraordinary Professor Meng today. Despite his world-leading accomplishments, he was remarkably humble and an easygoing character. I had a terrifically enjoyable experience conversing with him. I hope you enjoyed it as much as I did. In today's episode, Xiao-Li filled us in on how he founded the Harvard Data Science Review to shape what data science could be in the years to come. He talked about how data science is a collection of disciplines, including statistics, computer science, philosophy, and many more. How data minding is understanding your data well before mining or modeling it. How there's no free lunch with data, trade-offs abound. For example, the very concept of data privacy is at odds with the inherently shareable nature of data. How data quality and quantity are often inversely related, and how cleaner data can be less valid to the real world. He also talked about the paradox that having more data often means greater confidence around the wrong estimate of the population mean, and how the Bayesian, Frequentist, and Fiduciary schools of stats each have their own respective pros and cons, and so they're all valuable to know as a data scientist. As always, you can get all the show notes, including the transcript for this episode, the video recording, any materials mentioned on the show, the URLs for Xiao-Li's Twitter profile, as well as my own social media profiles at superdatascience.com/581. That's superdatascience.com/581. Finally, if you live in the New York area and would like to experience a Super Data Science episode filmed live, then come to the New York R Conference, which will be held on June 8th through 10th. That's the New York R Conference, June 8th through 10th. Huge names in data science will be presenting there, such as Andrew Gelman and Wes McKinney. And to close out the conference on the afternoon of Friday, June 10th, I'll be interviewing Hilary Mason, one of the world's absolute best-known data scientists, live on stage, so you can react and ask her questions in real time. Should be tons of fun, and I hope to meet you there, or if not at this conference, then somewhere else soon. If you want tickets to the New York R Conference, you can get them 30% off with the code SDS30. That's SDS30. Thanks to my colleagues at Nebula for supporting me while I create content like this Super Data Science podcast for you. And thanks, of course, to Yvonne and Siebert, Mario Pombo, Serge Massis, Sylvia Ogvang, and Kirill Eremenko on the Super Data Science team for managing, editing, researching, summarizing, and producing another extraordinary episode for us today. Keep on rocking it out there, folks, and I'm looking forward to enjoying another round of the Super Data Science podcast with you very soon.